All right, welcome back. In this video, we're going to be talking about end behavior of rational functions, mostly so that we can produce a better sketch of rational functions, but also so we can answer some limit questions. I think that's actually going to be more common in AP Pre-Cal, but I think overall, understanding end behavior of a rational function is important so you can understand the nature of its graph. But first I want to talk about the function f of x equals 1 over x. That's one that's going to be really important, I think, for our understanding here. And I am assuming you've seen this function before, maybe in Algebra 2, but just to remind you what the graph of 1 over x looks like. It looks about like this. So, I think the left half's a little better than the right half, but what's important is that when x is positive, f of x is positive, but decreasing towards 0. And that makes sense, right? If we're taking 1 and dividing it by larger and larger numbers, the quotient that's going to be left is going to be a smaller and smaller positive number. Okay, and then when x is negative, we're going to see the same behavior, except the outputs are going to be negative. We're going to be below the x-axis on the graph, but the more negative x gets, the bigger the denominator, the smaller the fraction gets, and it heads to 0. Now, last year what we said was that, okay, that means that this function has a horizontal asymptote to its graph at y equals 0. But then this year in AP Pre-Cal, we're talking more about limits, and so, the equivalent limit notation for that would be talking about the limit as x approaches infinity or negative infinity. And so I think that this is going to be important for us to understand why certain rules are going to be the way they are about rational functions with the degree of the numerator and the degree of the denominator. Now back to the notes, the key fact here, this is one of the AP Pre-Cal essential knowledges, is that the end behavior of a rational function will be entirely determined by basically the degree of the numerator versus the degree of the denominator. And as a result, the end behavior of a rational function can be understood by examining the corresponding quotient of the leading terms. I'm going to be very explicit about what they mean by that, going forward through these notes, but it seems like this is the officially approved AP Pre-Cal technique for determining end behavior of a polynomial, so I'm going to do it that way. I am going to also show you a probably more mathematically legitimate way of showing that these things are true. All right, now the first fraction I want you to consider is 10x over x squared. And I know we could simplify this if we wanted to, but I think that on a numerical level it would be a little more powerful for us if we actually just investigate what happens as x increases. So over here, 10x, that's just growing really fast, right? 10, 20, 30, that's much faster than x squared at first. But what we're going to do is we're going to let x, increase. All right, but it's probably going to go a little too slow for me to just increase one at a time. So I'm going to go from 1 to 3 to 8 to 10 to 200 to 1,000. I think you'll see the picture here. Okay, if I do 3 times 10, that's 30, 80, 100, 2,000, and then 10,000. Okay. And then I'm going to be dividing by x squared, so that's 9, 64, 100, 200 squared is going to be 40,000. And then 1,000 squared is 1 million. So what I'm saying is, as x gets really big, the x squared is going to be much, much larger in value than the 10x. And so what matters is the fact that the exponent on the x squared is higher than the exponent on the x to the first. Okay, and so we're going to be able to determine the end behavior by taking the quotient of the leading terms, is what they say. Now this only has one term in top and bottom, so it's not going to be that big of a deal. So I'm going to say 10x over x squared, and this is something I can simplify. That's equal to 10 over 1 power of x. And we need to be able to recognize, hey, this is a lot like 1 over x, the numerator is staying constant, the denominator is growing. The horizontal asymptote will be y equals 0, and so will the limits as x approaches infinity and negative infinity. And we will see that for any rational function of the type where the degree of the denominator is greater than the degree of the numerator. All right, there was another example in the notebook right there, but it was one where the degree of the numerator was exceeding the degree of the denominator, where it was a greater degree on top, and we're going to investigate that in depth in the next lesson, so I'm just going to save that for then, right? Save that all for a different day. So for now, I've got 2x minus 1 over 5x plus 1. Okay, and with this one, I think I'm going to make another table, but I'm just going to flash it up on screen. No, I've had a better idea. I'm going to let technology make the table for me. So I'm going to go over here and I'm going to type in 2x minus 1 over 5x plus 1 into y1. Then I'm going to go ask for a table. So I'm going to go over here to table. And okay, see how it has 0, 1, 2, 3, 4? I don't really like that. I want to add my own numbers to the table. So I'm going to go here for just table settings. And I'm going to have it ask me for the independent variable. And then I can just go over to the table and I can type in, no, I do not want a graph. Okay, I just want a table. Okay, and now I can type in my own values here, and I think I'm going to like that a little bit more. So I'm going to type in 1, okay, and I'll get 1/6. Okay, let's try 10. Okay, 19 over 51. Can we get these in decimals? What if I did something like 37? 73 over 186. I don't love this. Let me think. Just let me see if I can get it to work. All right, this is some calculator knowledge I didn't have before. You go to mode, answers. That's going to take a while. And then decimal right here. Okay, now it's going to give me decimals. I'm going to go back to the table because that's what I need. I need these decimals. Okay, so 1, 10, 37. Let's do, I don't know, 400. 3993. Okay, see, notice how more decimals are staying the same. And so then I'm going to do, I don't know, 1000. And that's 3997, maybe 5000. 3999. Okay, so you see what we're getting closer and closer to the bigger x gets. We're getting closer and closer to 0.4. So maybe I'll do 9999. Okay, there we go, 0.4. Okay, that's definitely round off error, right? It's not exactly equal to 0.4. Okay, what's really going on here is that the bigger x gets, the less important this -1 and +1 are to the overall total. And that's why we're seeing more decimals are staying the same, and we're getting closer and closer to to 0.4, which is equivalent to 2/5. So that's why we're going to go over here, grab the leading terms, the terms that have the highest exponent, and we divide them. So 2x divided by 5x, that's like 2 over 5. And that's going to be equal to 2/5 for any value of x that's not 0, but we're interested in the end behavior of this thing. Look at the values in the table. Like, we're interested in large values of x, definitely not values of x at 0. Okay, so that means that the horizontal asymptote of this thing will be y equals 2/5, and that'll also tell us the limits. And so, we're going to repeat these two situations, a few more times in this video, but that's pretty much what we've got going here, is the two situations with the horizontal asymptotes, when the degree on the bottom is bigger and when the degrees are the same. All right, so the situation we were just looking at with the 2x minus 1 over 5x plus 1, that's where the numerator and denominator have equal degree. And so if the degree of the numerator and the degree of the denominator are equal, then the quotient of their leading terms is a constant, like we saw, and that constant indicates the location of a horizontal asymptote on the graph of the rational function. Okay, and we're gonna do this a few times. I'm just gonna give two examples right here, one for me to do and explain why this works a different way, and also one for you to try on your own. And then there'll be more examples after that. All right, so the first one I've got right here is f of x equals x squared plus 2x plus 3 over 4x squared plus 5. And if you were asked, like, okay, what's the equation of the horizontal asymptote to this function, I want you to be able to look at this and be like, okay, same degree on top and bottom. I'm going to divide the leading coefficients, and it's going to be 1/4. So I got y equals 1/4. That's a problem that we could solve really quickly. But at the same time, that's not all that legitimate, right? It's like, wait, why does that even work? And so I'm going to show this to you in the context of a limit. But, it's going to make use of that thing that I started off with, the thing about 1 over x. So let's go ahead and do some algebra on this. So if I'm interested in the end behavior, that's really the limit of the function as x approaches infinity. And with rational function, it's going to be the same as if x approaches negative infinity, provided that we're sticking to these two situations, right, where the degree is bigger on bottom or equal. Okay, and what I'm going to do is I'm going to say, okay, well, the limit of the function is going to be the same as the limit of the function multiplied by a special form of 1. The special form of 1 is always going to be, if you want to, show this to be true, it's always going to be 1 over the biggest power of x that you see in either the top or the bottom. Now, the biggest power I'm seeing is x squared, so I'm going to divide top and bottom all the terms by x squared. And so I need to distribute that 1 over x squared to each of the terms as I go through. And so I'm going to say this equals the limit as x approaches infinity of, okay, I'm distributing the 1 over x squared, that would be 1. 2x over x squared, that's like 2 over x. And 3 over x squared divided by, okay, 4x squared divided by x squared would be 4. And then 5 divided by x squared, well, that's 5 over x squared. Okay. And now, for each of these fractions that I'm going to throw parentheses around, I want you to think about what's going to happen to them as x approaches infinity. These are all fractions where the numerator is staying constant and the denominator is growing. And at the beginning of the video, the very first thing, we talked about f of x equals 1 over x. And I hope we agreed that the limit of that was 0. And so the limits of all the rest of these are also going to be 0 for the same reason. Anything that's, inside of the red parentheses. So what this limit comes back with as x goes to infinity is going to be 1 plus 0 plus 0 divided by 4 plus 0. And that's equal to 1/4. And so that's the real reason, behind the, we're just going to divide the coefficients, shortcut, is that we could go through and do this this algebra on the limit every time. And now that we're doing limits as x approaches infinity in pre-cal, I think this is really good, and it's right at your level, so I can show you this and say that's why it works, but we don't have to do that. Let's do a different example. All right, so I'm going to give you g of x equals 2x to the 3 plus 12 over 6 plus 12x to the 3. And I'm going to also show you off to the left kind of the work I expect people are going to be showing, I don't expect you to go through all that limit work I did in blue. You're just going to divide the leading terms. They can ask you about the end behavior in terms of a limit or in terms of what's the equation of the horizontal asymptote, and we need to be ready for both, so I was just going to point that out. So why don't you find the limit as x approaches infinity of g of x, and also find any equation of a horizontal asymptote to the graph of g. We'll do that with video pause, because I'm just going to bring in the answers here in a second. All right, there you have it. So I'm going to divide the leading terms. That's 2x to the 3 divided by 12x to the 3, and I wrote it a little bit different, so we have to be like, oh, okay, it's the biggest exponent term on top and bottom. So that's the 2x to the 3 on top and the 12x to the 3 on bottom. That simplifies to 1 over 6. Okay, that means that the limit of g of x is 1/6, or the horizontal asymptote to the graph of g is y equals 1/6. And now we're going to go back to the situation where the denominator has the larger degree, which is kind of where we started. So if the degree of the denominator of a rational function is greater than the degree of its numerator, then the quotient of their leading terms is a rational function with a constant in the numerator and a non-constant polynomial in the denominator. Okay, which is exactly what we're talking about. The numerator is staying the same while the denominator is growing. And the graph of the original function has a horizontal asymptote at y equals 0. And this is an essential knowledge, so we just freely use this. We don't have to cite any sort of special knowledge or justify our answer. We're going to be just satisfied to look at something and conclude about its limit or its horizontal asymptote. All right, so the first example I've got one clearly bigger denominator on bottom. Okay, I got x plus 5 on top and 9x to the 2 plus 2x on bottom. Okay, so I've got quadratic on bottom, linear on top. Okay, and I'm going to do the same thing. I'm going to even use blue ink. I'm going to compute the limit of f as x approaches infinity. And much like last time, I'm going to, multiply by a clever form of 1 over the biggest exponent I see, right? So 1 over x squared, okay, either on top or bottom. And I'll probably be doing the same thing in the next video when we deal with the bigger on top situation. Okay, now if I distribute this 1 over x squared over the x and the positive 5, I'll have x over x squared is 1 over x. 5 over x squared will just be 5 over x squared, and then do the same thing in the denominator, rewrite. And then, much like last time, I'm going to go and I'm going to block off some fractions with red parentheses. And the idea with the red parentheses is these are fractions whose numerators are constant and denominators are growing as x approaches infinity, meaning those fractions that are blocked off in red parentheses, they're going towards 0. So this limit is going to equal 0 plus 0 divided by 9 plus 0. Well, that's 0 over 9, and that's going to equal 0. And so that's why we can just freely say, grab the leading terms, divide them, simplify, look at it, and see, okay, this numerator is constant, denominator is growing, horizontal asymptote is y equals 0, and the limit of the function is also 0. All right, now this next page, I kind of just decided to record this video talking about limits all throughout. I think when I made these notes, I thought I was going to only talk about graphs and horizontal asymptotes up above and then talk about limits more. I probably envisioned myself having, like, I don't know, some large amount of time to deliver the lesson. I did not have that much time in class, so I had to kind of do it all together. I didn't think it was that big of a deal. So when the graph of a rational function f has a horizontal asymptote at y equals b, the output values of f get closer and closer to b as input values increase or decrease without bound as x approaches, negative infinity or positive infinity. Okay, and then the corresponding mathematical notation is that the limit as x approaches infinity of f of x, or approach to negative infinity, it's going to equal b. That's what it means for the limit to equal b. We're seeing more and more decimals stay the same. We're approaching one particular value the bigger x gets. Okay, so what I'm going to do is I'm going to kind of like look at this just in the context of thinking about it in horizontal asymptotes. Down below where it says, why does this work? Well, I already showed you that. That's the stuff I did in blue where I was, dividing by, the biggest term I saw and showing that terms went to 0. That's not going to be necessary here. Okay, what we're going to do is maybe expand it out and think about the ratio of the leading terms, if we need to. All right, so right here we have x approaches infinity of x squared over 3x squared. Okay, we're going to do the end behavior thing, and so that's x squared over 3x squared equals 1/3. So we're going to say that limit equals 1/3. And then over here, well, this one I'm going to need to do a little bit more work on this one. So this is the limit as x approaches negative infinity. And now at this point in this unit with rational functions, I don't really care if x is going to infinity or negative infinity. It's not going to matter. It's going to be the same consideration regardless. With rational functions that are, pardon me, equal degree or greater degree on bottom. Okay, when the degree on top is greater, this will matter whether we're going to infinity or negative infinity. But for now, there's no difference. So this is going to be, if I was to square 2x minus 5, I'd have 4x squared, plus some other stuff. So I'm just going to write that out. 4x squared plus some other stuff. Divided by, now if I multiply x plus 1 times 3 minus x, I would have negative x squared and other terms. But all I need is the highest power term if I'm trying to determine the in behavior of a rational function. I'm going to go over here to 4x squared divided by negative x squared equals 4 over negative 1. So that limit is going to be the same as the limit of 4 over negative 1. Okay, that's just negative 4. Okay. And I already showed you how that works. All right, now here's two more. I think that these should be, a little easier. Notice on the left, I've got 3x minus 1 versus x squared plus 1. Okay, so I've got a greater degree in the denominator. Those always go to 0, right? So I'm just going to say, all right, if I had to do the officially approved AP Pre-Cal way, I would say I'm taking out the leading terms to determine my end behavior, and that's equal to 3 over x, and that goes to 0 as x approaches infinity. So I can use, or as x approaches negative infinity, right? There's nothing special about the fact that that would be a negative large number, except for the fact that it would be approaching 0 as a negative number. So negative 0.1, negative 0.01, negative 0.001, more and more decimals staying 0 the farther I go. So that's going to equal 0, and on the right it's the same story, right? Because it's degree 2 on top and degree 4 on bottom. Okay, so I'm actually just going to write degree 2 over degree 4, and that limit is going to be 0 because, for all the reasons that we've discussed already. All right, now to what we had said originally was kind of our goal, sketching the graph of a rational function. And I think I'm just going to do, I am going to do a couple of these, but I'm going to go pretty fast because this is not ever something that we're going to have to do on a quiz or a test in AP Pre-Cal because that's just not part of our free response responsibilities here. Okay, so what I'm going to do, I'm going to actually start by making a sign chart. Label it with my key numbers. Fill in the signs, and I'm just going to do this because you've seen me do this many times before. Notice the sign of y will not change at x equals negative 1 because it's a double root of the denominator. It's just the same as in the last unit when we had double roots. The sign didn't change. It's to be the same even if it's a double vertical asymptote. Okay, then I'm going to label my zeros Okay, so the zeros are x equals 2 and negative 3. And I'm going to use red for the graph. So negative 3 and positive 2. And then from here, I should probably also label the vertical asymptotes, which is going to be x equals negative 1 and x equals 4. I also know, now I'm talking about vertical asymptotes, and I've already told you about horizontal asymptotes. You probably think about that as well. Okay, because the degree on bottom is going to be 3 and the degree on top is 2, I know that y equals 0 is also going to be a horizontal asymptote. So I'm just going to kind of put in a dotted line here. This is my horizontal asymptote, y equals 0. All right, so for all x to the left of negative 3, the function's negative, but it's approaching a horizontal asymptote. So that means that it has to be looking kind of like that. Okay, that's not a very good drawing, but I think that'll just have to do. And then it stays positive on the other side of that vertical asymptote. Okay, you may have seen that called like togetherness or something in Algebra 2. And then I'm going to pass through 2. I don't know that we necessarily have a point of inflection at x equals 2. But I think in order to go from that vertical asymptote to the other vertical asymptote smoothly, which I know that we would have to have a point of inflection in there somewhere. Okay. And then positive forever after that. So there we go, and it's going to approach that horizontal asymptote. I actually know it's not going to cross the horizontal asymptote, because if it was, then I know I'd had another 0. Okay, and that's a good, decent sketch of a rational function. I'd say the only thing that could maybe make it any better would be a y-axis. And so I'm going to come through here and just the best I can try to draw a vertical line. Snapped 2 looks really good to me. That's a perfectly good sketch. I think that's the only one of those I'm going to do. Besides, to remind you about this situation, I'd forgotten about this. I put this in the notes. Okay, it's gonna, yeah, didn't like that. Okay, that's gonna equal x minus 5, x minus 4 divided by x minus 5. And then we could cancel these off, right? And there we'd be left with a hole in the graph of y equals x minus 4 at x equals 5. All right, so that's easy enough to draw. We're going to come back up through here at x equals 4. We're having a 0, and then there's a hole in the graph right after that, and then it resumes being linear. And you see that was pretty easy rational function to sketch. So don't forget about those either. All right, now the last couple of problems I've got for you, just a few examples related to asymptotes and limits, and I'm just gonna bring the answers into these onto the screen. You can work these with the video paused. I'm not gonna give a whole lot of explanation on these. If you want more, you can come talk to me, like before school or something, and I'd be happy to work with you on these. All right, so the graph of the rational function f has asymptotes at x equals 3 and y equals 5. F of x is always positive, or at least 0 for all x. Find the values of the limits. All right, so x approaches negative infinity, that's in behavior. Limit as x approaches 3 from the positive side, that's a vertical asymptote like we talked about last time. Get yourself a hypothesis, because the answer's coming here in 3 seconds. Okay, there you go. So in behavior, that's like the horizontal asymptote. Y equals 5 is a horizontal line. So we say the limit as x approaches negative infinity of f, that's going to be 5. And then as x approaches 3 from the positive side, well, I know that's going to be positive infinity because I've got a vertical asymptote at x equals 3. So it's not going to, the limit's not going to, exist and be a real number. And then they said f of x is always positive, so I know that means it has to be going to positive infinity. If it's approaching an asymptote and it's not negative, right, that's going to have to go to positive infinity. Right, here you go. I think I'm gonna copy in my extremely detailed work for this and let you check your progress against mine. This one's a little more challenging though, so give it a shot with the answer, or with the video pause. The answer's coming in a couple seconds. All right, there you go. So I use the vertical asymptote to determine the value of b, the horizontal asymptote to determine the value of a, and then the y-intercept to determine the value of c. In this next one, you're going to sketch the graph best you can on the provided axes. Give that a shot. Here comes the answers. All right, there you go. I give up. This program is keeps snapping this to part of a curve, and it keeps like looping back on itself. Like right there, I know it's not a function. I just can't seem to draw it and make it stay that way. I've given up, and that's my sketch of that graph. The thing we need to be careful about is the kind of the specifics about the nature of the vertical asymptote. I know in class one time I messed this up. I just wasn't looking at that closely. That we need to be going to positive infinity as we approach from the negative side, and negative infinity is from the positive side. And just got to be careful about those. And then here we got some mixed limits. Okay, so let's just do 4 at a time. Here's 4. Work these with the video pause. These are mixed, though, right? We're going to have vertical asymptotes, horizontal asymptotes, polynomial end behaviors at this point. I'm sure there's other types of limits I haven't thought of, holes, right? So be aware of those. Work these on your own with the video pause. Check your answer against mine. Here they come in just a couple seconds. All right, there you go. So of the first 4, 3 of these were limits as x was approaching infinity or negative infinity. I had to work those in red intentionally because when you see that, I want you to think about end behavior, either of a rational function or a polynomial. And I think it's pretty obvious when you're dealing with which. Okay, but as x approaches 1, that's not end behavior. Okay, so we have to try plugging in. And what we get when we plug in will determine our course of action. If we get 0 and 0, we're probably going to need to factor and cancel. If we get number over 0, we're going to need to do sign analysis because we're sitting on a vertical asymptote. If we get some other number, then our job's done, right? All we had to do is plug into the limit. All right, so try these 4. These are the last 4. Try these limits on your own once again with the video paused, and I will just bring in the answers here in a moment. All right, there you have it. So, okay, again, 1 vertical asymptote, that makes sense. That wasn't really part of the lesson today, that was more last time. And then 3 of these end behaviors. And if we just grab the greatest degree term on top and bottom and divide them, according to AP Precalc, we can't go wrong, right? So I think we just need some examples on the limits and a lot of examples on those asymptote problems. We'll be good to go. Okay, so that's going to be all for this video. Thanks for watching.